So last time we stopped here, we were talking about the ideal transformer, and we said that with the ideal transformer we have, let's we have current flowing on the primary side coming in. This current is because we have a voltage source here, and because we have a number of turns around this core. Again, current is flowing in this direction, so we are into the page, right? So we are into the page on this side, and then current is coming out here, right?
Yeah.
It's supposed to be coming out here. It's supposed to be coming in. This is supposed to be coming out of the page. Sorry, I think this winding is drawn incorrectly. These are supposed to be coming out of the page, okay?
The windings?
The current. The current coming out of these windings is supposed to be coming out of the page. Why? Because, again, when we remember when we talked about Ampere's law, we said that H dot dl is equal to what? I enclosed. No. Ampere's law has nothing to do with the transformer.
Yeah.
Right? Ampere's law just says that H dot dl is equal to I enclosed. The integral of the magnetic field intensity along a closed path, any closed path, is equal to the current enclosed by that closed path. Right? And then we said that this is our closed path where mutual flux will flow, right? Assuming mutual flux is needed to flow. In an ideal transformer, we will find out that mutual flux is not going to be needed because there's no reluctance to or there's no impedance to the magnetic field flow. So it's as if you have a short circuit across a voltage source that's of a picovolt, for example, right? As soon as you put a picovolt on there, infinite current will flow, right? If that source can provide that amount of current, right? So if you have a voltage source across with a short circuit across it, regardless of how much voltage you placed here, picovolt, nanovolt, whatever voltage you place here, infinite current will flow if the source can provide it, right? So it's like you don't need any voltage for current to flow, right? So sort of the same idea here. If I assume that the core is ideal, then I sort of don't need any mutual magnetic flux to be able to create the voltages on both sides, right? That's sort of what it means. We'll look at the equations that will help you. But basically, what this is saying is that the length of this path is length of the core. So, and the magnetic field intensity enclosed, we'll call that Hc in the core. H, so, we said B equals mu times H, right? So the magnetic field intensity is created by the flux density that's flowing, and this flux density B is equal to phi over A, right? B is equal to phi over A, flux density, right? So here we know that the flux that's flowing and the flux density are proportional, and their inverse of proportionality is the area, or proportional with respect to the inverse of the area. The B and the H are proportional with respect to mu. Here we're assuming initially mu is, let's say mu is constant, right? So let's see what that means, and I think we'll draw the BH curve next on the next slide. But for now we know that B and H are basically related, right? And then so this H, the integration of the H will be due to the flux that's flowing in the core, and that we will call H core. For example, let's call it H core. And the length of this path will be the length of the core, okay? And that will be equal to I enclosed. I enclosed will be whatever is enclosed by this path. We have a certain number of turns on the primary N1, certain number of turns on the primary N2, with current flowing in the primary and current flowing in the secondary, right? So, and they're opposite in direction, so I will have the currents are opposite in direction inside the core, inside the closed path. So N1, the turns on the primary multiplied by the current in the primary, minus the turns in the secondary multiplied by the current in the secondary, right? So that is what's enclosed. This is the amount of current that we have in this closed path here. Okay? If this N1 I1 minus N2 I2 is equal to 0, it means that my current in the primary, or my ampere turns on the primary, are equal to my ampere turns in the secondary, right? So assuming these number of turns in the primary and the secondary are the same, for now, let's say it's a 1-to-1 transformer, what does that mean? No, it means that the current in the primary is equal to the current in the secondary, right? Whatever current I'm putting in is whatever current I'm putting out, right? So the same voltage will be at the input, same current. Same voltage will be at the output, same current, right? So whatever is coming in is whatever. So that means the efficiency of that device is what? 100%, right? The efficiency of this device in this case is 100%, because I assume that there are no losses at all. So the core has infinite permeability. So the permeability mu is infinite. So it has the permeability and reluctance are inversely proportional, right? So the reluctance of the core, which is this R, we said that this is equal to what? I enclose ampere turns. We said that ampere turns H dot L, or the magnetic force, is equal to the flux times the reluctance, right? So the flux exists, but the reluctance is the inverse of permeability, and permeability is infinite, so reluctance is 0, right? So for an ideal transformer that has infinite permeability and reluctance are inversely proportional. So if this is infinite, that means the reluctance is 0. If the reluctance is 0, then basically I don't need any magnetomotive force, which is equivalent to voltage in an electrical circuit, to be able to push current. That's what this whole ideal transformer thing means. Okay? Is this real or not? It's not real, right? This is just an ideal representation of the transformer. So here I completely ignored any need to set up this magnetic flux. I set up this magnetic flux for free, basically, which is not true, right? So we will look at what the real equation is, but versus the ideal transformer. But we will use the ideal transformer approximation a lot. But what the ideal transformer tells us is that ampere turns in the primary is equal to ampere turns in the secondary. It also tells us what? It also tells us that the power on the primary is equal to the power on the secondary. So the voltage on the primary multiplied by the current on the primary is equal to the voltage on the secondary multiplied by the voltage on the secondary. All of this stuff, this is what this tells us, right? Whatever power I put in is whatever power I take out, because there's no extra current needed to produce the same current on the secondary side, right? So everybody's okay with this? Yes? Okay, let's move on. So some of these relations that we were just discussing are rewritten here, or the description of what we were talking about is rewritten here. So we ignored also the other thing that we ignored was there are no power losses, neither electrical losses and winding losses nor magnetic losses are present. So which means that there's no resistance between the voltage source and the voltage that is created across the terminals of this winding that's wrapped around the core, right? So we ignored that for now as well. So the voltage that is created at the terminals of the winding wrapped around the core is this back EMF voltage E1, and this back EMF voltage E1 we said is equal to N d phi by dt, and sorry, this is supposed to be E2 here, right? So this is the voltage on the primary, this is the voltage that is generated on the secondary, okay? And if we divide them by each other, the ratio between them will be N1 over N2. So d phi, the same flux flowing in the core. So if you put D1 divide by E1 by E2, you get N1 divided by N2. And because we said that we put a voltage, and this voltage is what we see around the coil as well at the core, and we ignored any impedance here, or the resistance of the copper wires, we ignored it for now, then this V that we put here is equal to E, right? So for now only. Right? For the ideal transformer, V will be equal to E. Right? So here, so that's why we said V1 over V2 is equal to N1 over N2 is equal to E1 over E2. And we can write this in, again, this is a sinusoidal signal with a certain frequency, 50 hertz, for example, so we can write it in phasor domain, right? Or write the RMS value of it, or whatever, right? So in phasor, we can rewrite this in phasors as, just use capital letters to represent phasors. Yeah. So that's what we have for the ideal transformer. And so we said that N1 minus N2, N1 I1 minus N2 I2, which is basically the current enclosed by the magnetic path that we have in the core of the transformer, is equal to 0 in this case, because this is equal to phi times the reluctance, and the reluctance is equal to 0, right? So that's why this is equal to 0 in the case of the ideal transformer where we have no losses, and we get this relationship. And we can rewrite this in terms of, rearrange, put I1 over I2 is equal to N2 over N1. So, which is equal to E2 over E1, right? So the current and the voltage are inversely proportional, right? So it's like a gearbox, right? So you put a certain voltage and current, the transformer either step up or down the voltages and currents, but it will maintain the power. Okay? So everybody's okay with this?
Sir, these relationships only hold for ideal transformer.
Yes. Now the voltage generated at the winding E1 and E2. No, this is true for any transformer. What we will add now is the impedances here in the path, right? So that will change the. So we will have E1 over E2 is equal to N1 over N2, but that will not equal V1 over V2. That's what we will add next. Okay, so right now for the ideal transformer they're equal, right? But what we will add next is we will remove that equality in the ideal transformer, in the non-ideal transformer case. Everyone's fine with this? We drew the phasor diagram for this before. I also have a small typo here. So remember what the phasor diagram, we said that we have a voltage source that is going to push current in a winding that is wrapped around the core. This is V1, this is E1, this is E2. V2 is the terminal voltage of the transformer. So as soon as I put a voltage, I will have current flowing. This current will flow to do what? Why will this current flow? To set up the magnetic field. Right? It's going to set up a magnetic field. It's going to set up a time-varying magnetic field. Right? So we said that any circuit, any component, or any physical system can be represented electrically as either an R, L, or a C. Right? If energy is being stored in terms of flux around the component, or in terms of flux, then we represent that component as an inductance. If energy is being stored in terms of charge, then we represent that component as a capacitor. Right? So here what we're doing is pushing current that is generating a flux that is flowing in this core. This core, this flux will be the reason we will have energy transfer across the transformer. So we will represent that as an inductive element. So it's like current flowing through an inductor. Current flowing through an inductor, what is the relationship between current flowing through an inductor and the voltage that created it? Sure, V is equal to L di by dt. So the relationship, they are going to be phase shifted by each other with 90 degrees, since we're talking about sinusoidal signals, right? So which is going to be leading, which is going to be lagging? Current lags, right? Because again, current in this case is equal to 1 over L integration of the voltage, di by dt, right? So you will take small pieces of the voltage and build up your current, right? So current will always lag the voltage. You have to have voltage there to start building up the current. You have to integrate the voltage to do that. So current will be lagging. So this is actually my V1 voltage that I've placed here, right? And since I ignored any impedance here, this V1 is also equal to E1. There's another typo here. Okay? This V1 is also equal to my E1 here. Right? They're equal. There's no impedance between them. For now, there's no impedance. So this is my V1 and E1. V1 and E1, I put V1, which is in this case equal to E1. But what was the consequence was current was flowing in the core, and this current created some magnetic flux that was flowing in the core. Hence, the current that resulted was 90-degree lagging from the voltage that created it. Because I'm creating flux, storing energy in flux, meaning I have an inductor representation. So, and this flux is related to the voltage at E to E1 with a certain relationship as well, right? E is equal to N d phi by dt, right? So if this is sinusoidal flux, if this is a sine wave, then the voltage will be a cosine wave, right? So it's also a 90-degree phase shift, but which is leading? The voltage in this case will be leading, right? So if this is a sine, derivative of the sine is a cosine, so cosine will be leading the sine by 90 degrees, right? So the voltage here, which is E1, is leading the flux phi, okay? And the same flux is also creating E2. The same flux is linking E2, is linking the second winding and creating a voltage across it as well. This voltage across it is related using the same equation. E1 and E2 are, assuming the number of turns are the same, they're related to the flux using the same equation. So d phi by dt as well. So also E2 will lead the flux. But if the number of turns are not the same, then the magnitude of E1 and E2 will be different. So here, in the general case, we put E1 and E2 the number of turns not the same. N1 does not equal N2. So in that case, E2 will be, different magnitude. It can be smaller or bigger, it does not matter, right? It just depends if this is a step up or step down transformer, right? And then generally, after that, if I connect a load, I will also have some current flowing in the secondary winding, I2. And this I2 will be coming in from the primary as well, because we said that N1 I1 is equal to N2 I2, right? So there will be a current I1 if there's a load connected as well. So here I just happen to have a load as well connected, and the power factor of that current, or the phase angle between the terminal voltage on the secondary side, which is V2 or E2 in this case, and that current will depend on the load itself, right? Because the primary current is related to the secondary current only by a magnitude. There's no phase shift, right? So if this has a certain angle phi, this will have a certain angle phi, right? There's no phase shift relationship between them. I will just take I2 multiplying by N2 over N1, and I will get I1, basically, right? So then this is where I've put my load, and since I step down the voltage on the secondary, and I have a certain current, that means I will step down the current on the primary, and the voltage will be higher, right? So everybody's okay with the phasor diagram, to a certain extent? Okay. So here's an example. We have a single phase, two winding transformer. Single phase two winding transformer rated for 20 kVA. So the power rating is 20 kVA. So this is my S for the transformer, right? And we said that we're only talking about ideal transformers now, so S1 is equal to S2. We agree? Right? The power on the primary side has to equal the power on the secondary side. This is a lossless transformer. Primary is 480 volts, secondary is 120 volts, so the turns ratio is what? This is 4 times, right? So N1 over N2 is equal to 480 over 120, which is equal to 4. And we have a 60 Hertz source. The source is connected to the 480 volt winding, supplying an impedance load connected to the 120 volt winding. So I have a voltage source connected here on the primary side, on the 480 volt side, and this is my 120 volt side. On the 120 volt side, I have an impedance Z2 connected. What do they tell us about this impedance? The load absorbs 15 kVA at 0.8 power factor lagging. So I can sort of I can draw the power triangle at the load if I want, right? So the load is 15 kVA, so I know it's a lagging power factor, so if I want to draw the power triangle, I will draw the power factor angle here equal to what? Inverse cosine 0.8, right? That's the power factor angle of the load. And then this is 15 kVA, so I can draw something to scale here equal to 15 kVA. That's equal to 15 kVA, right? So what can I do with this power triangle now? I can, since I have S and I have the power factor angle, then I should be able to find Q that the load requires, and I should be able to find P that the load requires. I also know this is a single phase load, then I can also calculate if it's connected to the 120 volts bus. So since it's connected to the 120, so I know voltage on my secondary side as well. So from S equals V times I conjugate, right? Knowing S, 15 kVA, and knowing V, I can calculate I as well, right? So I can calculate a lot of stuff right now, and they did that, obviously. They did that here. They calculated, you were given S, and you were given its power factor angle, and you were able to calculate I2 because of this power triangle that we drew up here, and the S equals V times I conjugate relationship. So we'll go through the solution that they did, but let's see what we can do without looking at the solution here. Assuming the transformer is ideal, calculate the following. The voltage across the 480 volt winding. So they told us that the secondary side has a 120 volt load connected to it. So what is the voltage on the primary side? Okay, what if they tell you the load is 100 volts? What is the voltage on the primary side? Huh? Exactly, it's 400. They just told you here it's 120 volts, so the voltage on the primary side is 480 volts, right? So the load impedance. So we have the power, we have the current, we have the voltage across the load. So we should be able to calculate the impedance, right? V equals I times Z. Knowing the voltage, knowing the current, we should be able to calculate the impedance. We'll look at the steps that they followed, but just want to make sure that this is clear. And then the load impedance referred to the 480 volt winding. This is something that if you didn't take 338, we will review it. We will look at what this means. But if you took 338 or are taking it right now, you may already know what this means, right? So I have a load connected to the transformer secondary side, right? This load corresponds to a voltage and current here, and there's a voltage here because I put a voltage source here, right? So if I want to know what the voltage across the load is, what did I do? I took my voltage source and multiplied it by 1 over the turns ratio, right? So I wanted to find what E2 is or V2 is, right? I know the relationship is E1 over E2 equal to N1 over N2, which is equal to 4 in this case, right? So if I want to find, if I'm putting a 480 volt source here, and I want to know what the voltage is on the primary side referred to the secondary side, what would I do? I would take the 480 volts and divide it by 4. Right? So E2 is equal to what? N2 over N1 times V1, right? Which is equal to 1 over 4 times 480, which is equal to 120 volts. So that is referring my primary voltage to the secondary, right? Same thing, I can take everything on the secondary side and refer to the primary, right? Assuming now I don't know that this box has a transformer. This is a box. This box is consuming current. I'm putting a voltage and it consumes current. What does that mean? It means that there's a load connected, right? So I can sort of figure out a way to, and this load, if I don't know it's a transformer, I can assume it's nothing but I know it's a, I will see a lagging power factor. So I will say, okay, it's a RL load. Is this right or wrong? It's right. It's what this transformer is seeing on the primary side, even though you don't know what's inside the box. I have no clue. This is what the transformer is seeing at its terminals. The terminals have to happen to be the primary side of the transformer. So like we referred the voltage on the from the primary to the secondary, and I can refer the current as well from the primary to the secondary, or from the secondary to the primary, I should be able to take my impedance and now refer to the primary side and see, okay, this is equivalent to having an impedance of the primary side equal to something. This impedance has to be consuming the same amount of power. Whether if I put it on the secondary side, it will consume S. Put it on the primary side, it will consume the same S. Right? So I have to find a way to do this transformation. Like the star-delta transformation that we came up with. At the end of the day, the two boxes consume the same power. Right? So let's look at the derivation for that, and then we'll come back to the solution. I think I showed the derivation on a slide later on. Sorry. Yeah, here. Okay, so here I have an impedance on the secondary side equal to Z2. Z2 is my impedance on my secondary side. It's a general R plus JX type impedance, right? I want to refer this impedance to the primary side. I want to see what the primary side sees. Assuming there's no transformer there, bring this impedance to the primary side, what will this value of this impedance look like? Right, so I have an impedance on the secondary side, Z. I want to put this in a box and represent this box using a RL circuit only. So the way to do that is figure out a way to take this impedance Z and refer it to the primary. The same way we did for the voltage and current. I know that for me to take my primary voltage from the primary side to the secondary side, I need to divide it by the turns ratio. If I want to take my current from the primary side to the secondary side, I multiply by the turns ratio. And I can do the same thing with the secondary quantities. I can bring them to the primary side as well, right? If I know this, I know that, right? So I need to do the same thing with the impedance. So how will we do that? We know that E1 over E2 is equal to A is equal to N1 over N2. That's the turns ratio. So A is equal to N1 over N2, turns ratio of the primary over the secondary. So E1 is equal to A times E2. And then I know that the currents and voltages are inversely proportional across the transformer. So I1 is equal to I2. I1 is the current on the primary side, and I2 is the current on the secondary side. So this is I1, this is I2, V1, V2, right? So this is N1, N2, N1 over N2 is my turns ratio A, right? So I know E1 is equal to A times E2, and I1 is equal to I2 divided by A. So from my equation for impedance, I know from Ohm's law, right? I know that V equals I times Z, right? That's the only thing I know. And I know that power on the primary side should equal power on the secondary side. If I take the impedance and bring it to the primary side, it will consume the same amount of power, right? So if I know that, then I can sort of say that the impedance referred to the primary side is equal to what? The impedance is equal to the voltage divided by the current. So I have my voltage on the primary side is E1. That E1 is equal to A times E2, correct? So I wrote A times E2 here. Instead of E1, I wrote, so Z2 is equal to E2 divided by I2, right? Z2 prime is what I would like to find out what it is, right? So basically that impedance refers to the primary side. So Z2 prime is equal to what? Is equal to putting this thing in the black box and looking at what the voltage and current I have on the primary side are and dividing them by each other to get the impedance that is equivalent to the impedance that I have on the secondary side. So then Z2 prime is equal to the voltage on the primary side divided by the current on the primary side, right? That's represented as a quantity using secondary quantities, right? E2 is a secondary quantity, I2 is a secondary quantity. But I've referred E2 and I2 to the primary side using A times E2 and I2 over A. So A times E2 is the voltage, I2 over A is the current on the primary side, right? This is my primary current now, right? But after I put this in a box, right? If you simplify, you'll get A squared E2 over I2, and you will get A squared times Z. So the impedance, equivalent impedance that this same voltage and current would have to feed is equal to that impedance on the secondary side multiplied by the square of the turns ratio, right? So remember, to refer the voltage and current, we multiply by turns ratio or divided by turns ratio. To refer the impedance, to bring the secondary impedance to the primary side, I'm going to multiply by A squared. To bring my primary impedance to the secondary side, I will divide by A squared. Right? I can do both. I can do this or I can do that. Okay, so this is the secondary impedance, R2, referred to the primary side. Secondary impedance, referred to the primary side. Okay? So basically in that in the problem that we were looking at, they're just asking you to apply this equation. There's no... So the load impedance referred to the 480 volt winding. So we were able to calculate the load impedance because we have the voltage and current to this impedance here, right? So we know what this impedance value is. I can take this impedance value that's calculated, multiply it by 4 squared, which is 4 is the turns ratio in this case. So that's what this one is. The real and reactive power supplied to the 480 volt winding. How would I do that? Not 20, because 20 is the rating of the transformer, yes. But the load is 15 kVA, right? So the transformer is rated for higher than the load. So they're asking what is the actual real and reactive power that is being supplied by the 480 volt winding. That's from the power triangle that we drew. Because remember, the real and reactive power, this is an ideal transformer. So the real and reactive power on the primary side is going to equal the real and reactive power on the secondary side. So we already calculated that from the power triangle. Right, so there's no need to recalculate that. So let's see what the solution looks like. Did they tell us what the voltage of the load is? Or? We did one mistake. We didn't look at this number. They said that the load is not 120 volt. The load is 118 volts. So what is the voltage on the primary side? Sorry. I said it was 120 initially. It's 118 times 4, not 120 times 4. Okay? So that was, I didn't look at that when I was reading it. That's why I have to read the problems very carefully. I was just, testing you, showing you that this is what happens when you don't read the problem carefully. Because there are too many numbers, so excuses. Anyway, but basically nothing changed. I mean, just that number changed. So the voltage on the secondary side was 118. I multiplied it by 4, which is 472. I used that as a reference. Since I didn't identify what is your reference, right? Again, references are, as long as, like in electrical circuits, right? In circuits, you drew this 214 circuit and you said, okay, this node is my reference. Based on what? Based on this, you wanted this node to be your reference. In a practical power system, you make this reference your ground in a practical power system, because you want to measure everything with respect to ground potential, because people are walking on the ground. If the potential is different than what the potential that they're walking across, then they will be electrocuted, right? So it makes sense to make this as a reference. In circuits, it's the same thing. So, but voltage of what does voltage reference mean? Voltage reference means that just this generator, I started this generator, okay? And then 1 millisecond later, I started a second generator right next to it. So the phase angle is really when this started versus when this started, right? So take one as a reference. Does not really matter. That's why in power systems, when we start making simulating bigger power systems on Power World, we will always have a reference. We create one generator. Okay, this is my reference. I'm always interested in angle differences and voltage differences, right? But I will make a reference, and I will make this reference have an angle of 0. That means all my other angles are, even though they're angle differences that I'm interested in, right? They're actually absolute values. They're absolute angles with respect to 0, right? That's the way we will go about doing things, right? So doing things. So that's why when we say, okay, 118 has an angle of 0, it does not really matter. You can take this as a reference. Our objective is to calculate the current and the impedance across this voltage. It does not really matter. The current and the impedance will not really care what the voltage reference is, what the voltage angle is at that point, right? You have a voltage, and you have an impedance. You will be able to calculate the current. From a phasor perspective, it's the same, because the current will lag or lead based on the value of the impedance itself, right? You put the voltage, you make it this direction. It doesn't matter. If you have a certain impedance, the phase shift between the voltage and the current will be fixed. You move the angle, the voltage 20 degrees plus or 20 degrees minus, does not really matter. The phase angle between the voltage and current will be the same, right? So I used 118 volt as my reference, since I was not given any other reference. I calculated my turns ratio to find my primary voltage. I multiplied by 4, which is my turns ratio, and then from our power triangle, I know my voltage on the secondary side now, and I know my load rating, right? So I know my voltage on the secondary side, 118, and I know my load power rating, and its power factor, and its angle. So from there, I should be able to calculate the current, and that's what they did for us here, right? So from there, we did calculate the current. If I know the current and the voltage and the load, right, I was able to calculate the impedance of the load, right? The next thing they said was, what is this impedance as seen from the primary, right? You don't need to do this A square transformation, by the way. How else can I do this? I know this voltage on the secondary, and I know the current on the secondary, right? Now, because they were asking for the impedance as referred to the primary side, right? So I have the impedance referred to the secondary side. I also have I have the impedance on the secondary side. I also have the voltage and current on my secondary side, right? They're asking what is the impedance referred to the primary side. You can go multiply by A squared, like we just derived. Or, again, if you know your voltage and current on the secondary side, I know my voltage, E2, 118 volts. I know my current on the secondary side, it is 127.12, right? I know E2 and I2, right? I know this is N1, this is N2, and the ratio between them is for N1 over N2 is equal to 4. Then I should be able to find E1. E1 is equal to E2 times 4, and I1 is equal to
1 over 4
I2 divided by 4. Exactly. Right? So then I have E1 and I have I1. If I have E1 and I1, take those and divide them by each other, you will get Z1, basically. The impedance as seen by the primary side. You can do it this way, or you can just multiply by the turns ratio squared. Take your impedance that you have on the secondary side here and multiply by A squared. Right? This or that, they're the same. Okay, so they did it by multiplying. And then they said they were asking for the real and reactive power. So our apparent power on the primary side and the secondary side are equal, 15 kilovolts. No, the 15 kilovolt was the load. Yeah, it's 15 kilovolts with a certain power factor, which is what we have here, and then that corresponds to, in rectangular form, to certain real and reactive power from the power triangle, which is the real and reactive power on the primary side as well, since it's a lossless transformer. Okay, so since it's lossless, this is also equal to the real and reactive power at the input of the transformer.
So why didn't they use? Can you repeat, please? Why did they didn't use the 15 kilo?
No, they did, but this is it has a power factor, right? So it's 15 kVA with a certain power factor. So let's see. Let's see. Why didn't they use? Good point.
Because you said the power should be
It is the same, and they say that here the complex power absorbed by the load is 15 with a certain power factor angle. But let's see what they did. They messed up. They copied.
They copied them.
They copied the impedance.
Yeah.
See, we found a mistake in the book. Good. You're always awake. That's good. So this should be 15 angle, same angle, 36.87. So, and they said that here. They said that here, but and I said it initially, right? I just didn't solve. So. Good point. Good point. Any questions? She's awake. She gets another half point.
Thank you, sir. Thank you.
No problem. Okay, so let's see. So now this is the ideal transformer, right? So we've been talking about this ideal transformer for a while, and it's interesting and all that. And we came up with the representation of the ideal transformer, where we said that we now understand all the relationships between the voltages and currents on the primary and secondary sides, right? What is the relationship between the turns ratio? A certain number that N1 equal to the ratio of N1 over N2. That's the relationship between the voltages and currents on the primary and secondary sides, right? If I have current on the secondary side, I2, and I want to find the current on the primary side, I multiply by 1 over the turns ratio, right? It's a magnitude. Is there an angle shift? Is there a phase shift in what's happening? Is there a phase shift between the currents on the primary and the secondary side?
No.
There is no phase shift. There is no phase shift in the ideal transformer, and in that we discussed. Now there is no phase shift. Okay, but and this is true when we talk about star-star transformers as well, in 3-phase, or delta-delta transformers as well, because this phase winding will be in phase with this phase winding. This phase winding will be in phase with this phase winding. Same thing with the delta. This phase will be in phase with this phase. This is the primary and this is secondary. This phase will be in phase with this one, primary and secondary, right? So they are related only by turns ratios. We agree? But later, when we talk about, later in this chapter, we'll start talking about star-delta transformers, right? In star-delta transformers, we will end up having something very funky, right? We will have phase shifts between the phase voltage on the primary side and the equivalent phase voltage on the secondary side. Remember, the delta, we will have to convert it to a star. When we convert the deltas to a star, we said that the voltages and currents, we will have to pay attention to the magnitudes and angles of voltages and current. There will be lots of square roots of 3s and 30 degrees. We will look at that later. Yeah. So, but we will have to convert these deltas to stars to be able to solve, because our objective is always to come up with a single phase equivalent circuit. That is our continuous objective, because that's what we know how to solve from 214. So to do that, I know that with a star-star transformer or a delta-delta transformer, like similar to the ideal transformer, that turns the ratio, or there is no phase shift between the quantities and voltages and current on the primary and the secondary side. It's only a real quantity or a magnitude relationship. But when we have star-delta transformers, when we come and draw the single phase equivalent circuit, where we have that transformer present and we have both turns ratios existing, and we have to take care of this phase shift somehow. So we will come up with a fictitious model for these star delta transformers that looks the same, two windings, but instead of having a real turns ratio, real number as a turns ratio, the turns ratio will be e to the j phi to 1, for example, or n1 e to the j phi over to n2, right? What does this mean? It means if I have current on the secondary side equals to I2, what will current on the primary side look like? I1 is equal to I2. If it's a ideal transformer, it's going to be I2 divided by the turns ratio, right? Same thing, it's I2 divided by the turns ratio, but in this case, the turns ratio has an angle, right? So it's I2, and here I made the primary side angle leading the secondary side. So the turns ratio will be such that the voltage will lead by 30 degrees, and the current will lead by 30 degrees. Everything you move from the secondary to the primary will lead by a certain angle phi, right? This is what this means. If I have e to the j phi to 1, that means any quantity on this side will be moved to this side with a phase shift, right? And we will do more of that with examples, etc. But it's something that, since we know what the model looks like, we wanted to show you this, and we discussed that here. So note that the phase angle of E1 leads the phase angle of E2 by phi. Similarly, I1 leads I2 by same angle phi. Every quantity on the secondary side, to move to the primary side, I will have to phase shift by angle phi. And here I'm making the primary lead. I can make it the opposite, right? I can make a secondary lead. Does not really matter. But there's actually a standard that we will follow. The standard says that the high voltage side leads. That's the American standards for naming conventions of transformers, right? So we will follow that the way the standard introduces it. Yeah. Anyway, so now this was the ideal transformer. So practical transformers. Practical transformers, we have to include the effect of the winding resistance, right? It's a copper winding, so it has some resistance. Again, the magnetic flux is not entirely confined to the core, meaning, you have the flux that's flowing in the core. This flux that's flowing in the core has another option. It can flow in the core, or it can flow through the air, right? So this is the core. Flux that initially you said is confined to flowing in the core. It's going to be either flowing in the core or flowing in the air. This is flowing in the core or flowing in the air. It's like, right? Current coming into two nodes. Current will be distributed based on Kirchhoff current divider rule, right? Some will flow here, some will flow here. The majority will still flow where? In the lower impedance, right? The lower impedance will definitely be the core, right? The reluctance of the core is a lot lower than the reluctance of air. So the lower impedance will definitely be the core, but there will still be some flowing in the air. So we want to consider that. Again, how do we consider flux that we have generated due to the voltage from the source? How is this flux generated? It's generated because of current flowing in certain windings developing a magnetic flux around them. Is this helping us link the primary to the secondary? This leakage flux? It's not. It's not helping us link the primary to the secondary. So I can represent it as a drop of the amount of flux available or produced by my source, right? So since I can represent it as a drop in the path of the voltage that produced it, then I will figure out how to add that in the magnetic circuit. I will sort of come up with a representation of this leakage flux as an inductor, and it's not helping me produce voltage at the output. It's actually hindering me. It's hindering me from producing voltage. The voltage that I put at the input, some of it is being used to create this flux that is just flowing in the air. So it's going to be a voltage drop. So it's going to be placed in series with the voltage source that I have at the input of the transformer. Same thing with the winding resistance. This winding resistance is also something that will be hindering me from pushing more current into the core to create flux, right? Useful flux in the core. So it will also be represented as a component that's in series, or a voltage drop in series with the source before reaching what? After that. So if I take care of the winding resistance, that's taken care of, and I take care of the magnetic flux, that is this air that's flowing in the air, then then where do I reach? Then now I'm at the core, right? So I've taken care of the resistance in the path, I've taken care of the flux in the air, then I need to look at what the core has. The core has reluctance as well, in this case. This core reluctance, is it something that I need to produce the voltage or not? Is this what I'm trying to feed, actually, to create in order to produce the voltage? Yes, without this magnetic core reluctance, without this flux in the magnetic core, I cannot link my secondary coil. I cannot. I have no way to do it yet. Right? And the voltage across this winding, E across the winding, is equal to what? N d phi by dt. What is this voltage? This is my voltage that is developed across the actual winding. So that's the voltage that I am actually seeing on my primary side and on my secondary side, assuming the same number of turns or assuming a certain number of turns. Right? So it's a component that has to be placed in parallel. Somehow. It's going to have to be placed in parallel with my output, because the voltage across it is what I have across the winding. Right? So the voltage across this specific representation of the flux flowing in this magnetic circuit. Right? So it has to be a parallel component, because the voltage across it is this voltage that I have developed, E1, on the primary side of the transformer. Versus here, no. The voltage across that's developed due to the leakage flux linking my coils. Right? This is leakage flux flowing in the air. There is this flux is linking a certain number of turns. Right? This flux, if it's linking turns, that means there's voltage developed across these turns. Right? This voltage is something that is actually not used to produce my output voltage. So it's a drop in the path of producing my useful voltage, which is the one across the magnetic core, or the representation of the flux flowing in the magnetic core, which is E. That's why I put the leakage flux component in series here. And the resistive component in series here, because it's just burning power. I don't care. It's not doing this transformer action that I'm trying to create. So it's also a series component that I have here. And then now I can represent my transformer action. My transformer action is basically the ideal transformer. After that, so I've taken care of the winding resistance in the primary, I've taken care of the leakage flux in the primary, I've taken care of the core magnetization. Now what's happening? Now this core magnetization produced E1 and E2. Right? It produced E1 and E2. So now I have my ideal, and these E1 and E2 are related by the number of turns. So now it's my ideal transformer. Right? So now I have my ideal transformer represented in here. And then I have something similar on the secondary side as well. I have resistance of the windings on the secondary side. That is really not useful. It's a drop in the path. It's actually not it's outside my ideal transformer representation. My ideal transformer said power at the input is equal to power at the output. It's only around here, this zone. After that, what's happening? After that, I'm losing some voltage drop because of the resistance of the windings, and it's burning power. So it's something that it's hindering me from producing my terminal power. It's something I need to subtract from my terminal power. So I need to put it in series. Right? It's not equal to my terminal power. It's subtracting from my terminal power. So it's in series. Same thing with, again, these windings have, after you connect a load, current will flow in these windings as well. Right? So before you connect the load, no current is flowing. After you connect the load, then current will start flowing. Current starts flowing, and then flux will be generated due to this winding as well, and you will have flux that is helping create the magnetic field, the mutual flux. This mutual flux will help develop the mutual flux, this N1 I1 minus N2 I2 quantity, right, is equal to some phi times the reluctance, right? It's equal to some N times the magnetizing current. This I1 minus I2 is equal to the magnetizing current. So some of it is creating that, and then some of it is just flux that is flowing in the air, right? It's basically losses here. So these losses I will also represent as as an inductor in series here as well, because they are not helping me produce the mutual flux. It's not helping me produce mutual flux or creating the transformer action, so it's something I have to subtract from my voltage at the terminals, right? So, and then we connect our nice load. Right, so now we took care of the winding resistance, we took care of the flux that is not confined in the winding, which is called leakage flux, both on the primary and the secondary side, this and this, here. Yes, sir.
So I didn't understand why the E1 is before the transformer.
It doesn't matter, you can put it here or here. What do you mean before the transformer? It's in parallel. It's in parallel with the transformer, the ideal transformer representation.
Yeah, but the E1 is the value of the secondary, right?
Equal to the voltage generated across the windings on the primary side.
How about the voltage generated on the secondary side? Does it,
We include that using the model of the ideal transformer, because this same flux is actually linking the secondary side and creating a voltage E2. And this E2 is related to E1 using N d phi by dt. Right? It's only the only difference, because since now it's the same flux, then there's the difference between E1 and E2 would be the number of turns only. Right? So, and we took care of that by putting the ideal transformer with different number of turns. So I have an E2 here. There is an E2 here. This E2 is related to E1. It's in parallel. E2 here and E1 are the same. Right? You just take care of the turns ratio of the transformer. I can bring it here. I can bring this, no problem. I can bring this impedance on this side, but I have to put it somewhere. I have to either put it on the primary side or secondary side, right? It does not matter. I can bring this impedance on this side, and we know how to do impedance transformations. And this impedance has a voltage across it here equal to E1. If you bring it here, the voltage across it to be E2. Because the current flowing through it here is what? Is the primary voltage divided by the impedance. Current flowing through it in this side will be the secondary voltage divided by the impedance, right? So the value of the impedance will be different, but we can put it here or here, and we will talk about that later. Okay, so we took care of the core permeability being finite and said that we have to have certain flux flowing, and this flux we will have to represent it using some component that will be drawing current that is not useful to creating my output, right? So N1 I1 minus N2 I2. Is it going to equal 0 in this case? No, it's going to equal phi times the reluctance. It will not equal 0. That means that if the n's are the same, it means that I1 is not equal to I2. It means that I have to put a little extra current on the primary side to get current on the secondary side, right? That's what this means. And this little extra current is going to be flowing here in this impedance that we have here, right? Also, there are real and reactive power losses in the core. Okay, so the reactive power losses in the core are basically what we have represented through this impedance, right? But we also have some real power losses in the core. These real power losses in the core are due to the fact that we have this mutual flux developed. So this is something that I will need regardless whether I have a load connected to the secondary or not. It's something that exists because I need to create a transformer action. So I have to put that in, represent that as a resistor in parallel with this flux as well. Okay? I need it. It's not a voltage drop in the path that will reduce the amount of flux that's flowing in my core. It's not. It's something that is actually I need it to create this mutual flux. I have to have it there. So I will represent it as something that will always exist with my voltage. Anytime I generate the voltage on a linking that is caused by the linking of the flux of both windings, then I will have this loss. Okay? It will exist. It will always exist. But if there's no load on the secondary, okay, if there's no load on my secondary side, right? If there's no load on the secondary side, and I represent these two components as something in series here on the secondary side, is current going to flow through them?
If you had no what?
If I have no load on the secondary side, so it's open circuit, right? And I don't put these branches in parallel, I put them in series. And remember, we said we can bring impedances primary side or secondary side, does not matter, okay? So I can take these two and I put them in series on the secondary side. Is any current going to flow through them? Current will not flow through them, but I need current to flow through them to create the voltage, the back EMF voltage E1 and E2. Even if current is not flowing on my secondary side, I still have E2. If you don't have a transformer loaded, the transformer is unloaded, but you supply its primary, you will see voltage on the secondary side because of N d phi by dt, right? So that's why these components have to be in parallel. They cannot be in series because they will have to have current anytime you have a voltage connected to the primary side of the transformer. Otherwise, you will not see voltage on the secondary side. And the equivalent circuit will not be a good representation of what you really have. Okay, so that's why they have to be in parallel. Parallel here on primary, secondary, doesn't matter. You can move from here to here. Okay? Is this everything that we have in the transformer? No. Right? Why is it not everything we have in the transformer? Remember we said we used H.dl is equal to I enclosed? Right? And then we from there we said that N1 minus N1 I1 minus N2 I2 equals phi times the reluctance, right? Which is equal to H core times length of the core, right? So we said that this is always equal to H core times length of the core, and H is equal to what? B equals mu times H, right? B equals mu times H. So we said that B, H, the magnetic field intensity, is due to some magnetic field density in this core created by the flux flowing. And we assumed this was a fixed number, right? Is this a fixed number? No, it's not. Is this linear?
No.
It's not. There's a BH curve as well involved, right? So what happens due to that? So let's... So we didn't consider it in this model. Stuff like this we didn't consider because now let's say in a, your typical BH curve that we have for a magnetic material looks like, let's say approximated for now, let's look like this without hysteresis. Okay, if it looks like this is B, this is H. Remember, H is equal to N times I magnetizing. H core is equal to N number of turns times the magnetizing current, which is equal to I1 minus I2, right? So this is proportional to current, and this is proportional to flux flowing, right? And flux flowing is generates corresponding voltage, right? So remember the flux, E is equal to N d phi by dt. So B equals phi divided by A. If B is not changing, is phi going to change? B doesn't change, phi will not change. If phi does not change, am I generating a back EMF voltage opposing the input and limiting my current? No, I'm not, right? So this can be a cause of inrush currents as well. And I don't represent this in an equivalent circuit. I don't have a way to represent it in an equivalent circuit easily. So I don't take care of that. What else am I not taking care of? I'm not taking care of the fact that, okay, E equals N d phi by dt. If this is a sine wave, then the voltage is a sine wave, right? But how about the current? The current is basically going to depend on what? Current is proportional to the H, right? So we said that B is equal to mu H. If phi is sinusoidal, I can assume B is sinusoidal since they're directly proportional. And then if mu was linear, then I would also get a linear relationship between B and H. So if this is sinusoidal, this will also be sinusoidal. But mu is not linear. It's only linear in this zone. And then there's saturation. So what will this do? It will cause a difference between the B and H shapes. So instead of B being sinusoidal, H being sinusoidal because flux is sinusoidal, because voltage is sinusoidal, then H will not be sinusoidal. Hence, the current that is producing this H in the core, which is the excitation current or magnetizing current, is not sinusoidal. And let's look at how we can derive that. So anyway, let's go through the slide. I have one slide on that. So here we added the resistance of the core, the windings. That's taken care of. And then here we looked at the leakage flux that we were talking about, and we said that it has to be represented as a series impedance, series inductance as well, in the path of the voltage. And then, you can apply Ohm's law here. Kirchhoff voltage law around the loop will apply. So E and V are no longer the same. There will be a voltage drop between them, right? So I hope that's okay. We talked about that. And then, what does this say? Yeah, here we're just calculating okay, so let's do that. Calculating the value of this parallel branch, the magnetizing branch. So starting from where? Starting from, we know that the magnetizing current is equal to N1 I1 minus N2 times I2, right? We said this comes from Ampere's law. Right? We said this comes from Ampere's law. And if the transformer is ideal, we said that N1 I1 minus N2 I2 is equal to 0, right? If it's not, if we have a real transformer, it's equal to the flux times the reluctance that we have flowing in the core, right? So now we were talking about the real transformer, not the ideal transformer. So I'm going to take this equation and divide it by N1, right? I'll divide by N1, divide by N1, and I rewrote it here. I1 minus N2 over N1 times I2 is equal to the reluctance times the flux divided by N1. Okay? This is the equation from Ampere's law. This is this equation here. And then this I can rewrite, so I can rearrange the terms. So the reluctance over N1 I keep outside, and then phi is equal to what? Remember our E equals N d phi by dt? And then we said that phi is a sine, phi max sine omega t, and then we differentiated to find the voltage E, and E was equal to j omega n times phi, right? So solving for phi is equal to E over j omega n, right? So that's what we have here. So I removed phi and put E over j omega n, right? And then, which is equal to, so bring the j to the top, so minus j over blah blah blah, right? So this is just rewriting the terms down. If I take this is equal to, so this I1 minus N2 over N1 I2, this is basically the current of the secondary side referred to the primary side, right? So taking I2, if I want to bring I2 to the primary side, I divide it by the turns ratio. So turns ratio is N1 over N2. So if I divide it by N1 over N2, it will be equal to I2 multiplied by N2 over N1. So that is the secondary current referred to the primary side, right? So that is the primary side current minus the secondary current referred to the primary side. That is equal to the magnetizing current, okay? Which is equal to this. I took this term here, I put here. So I have an equation here that looks like what? I and V and some impedance, right? My Ohm's law said V equals I times the impedance. So if I write it in terms of admittance, I can write what? Yeah, so V times the admittance is equal to the current, right? So because the admittance is equal to 1 over the impedance, right? So I bring Z on this side, so 1 over Z here, which is admittance. So Y times V is equal to the current. So this equation is written in that term, in that form. And my current happens to be the magnetizing current, and the voltage happens to be the voltage in the primary. So this is actually what? This is the value of that shunt impedance, the shunt magnetizing inductance that we have. That impedance that we have, the magnetizing inductance that we have here, this is what it's equal to. Okay? in admittance form. Okay, so it's so this is the susceptance component of the admittance. Okay, there will be a conductance component as well, which is going to be representing the R reluctance of the core losses that we have as well, right? So this is one component that we have in there that is that has the magnetizing current flowing through it. We also said that the core has a resistive loss. The resistive loss is due to the fact that the resistive loss is represented not because of the resistance of anything. It's because we have hysteresis losses and eddy current losses. These losses are gonna be real or reactive power losses. This is actually we said that eddy current losses is actual current flowing in the lamination material, which has some resistance and causing power loss. So it's a real power loss. So we represented that as this resistance in parallel with this magnetizing branch. So we have to represent that somehow. We have to find a value for it. And the current flowing through it is going to be, of course, 90 degrees ahead of the current flowing through the magnetizing inductance, right? It's going to be in phase with the voltage that created it, which is the primary voltage, the voltage on the primary side, right? So we have that. I think that's what we're going to be calculating next. So we calculated the reactive component, and of course the magnetizing current is equal to either E over JXM or minus J times E times BM, right? And then for the real component of current is in phase with the voltage that produced it, and we will represent it as a resistive loss. It's a resistive element that we represent in parallel with the transformer's ideal transformer. And if you want to represent it using admittance formula, it's E times the conductance component of the admittance, right? So admittance is equal to conductance plus susceptance. The susceptance component is equal to RC over N blah blah blah. It's actually equal to negative J RC over N over omega N squared. That's the susceptance component. And the admittance, the conductance component is this RC, and we will calculate it, I think, on the next slide. So, any questions so far? Yes, ma'am. Yeah.
They have to be there. Can you explain again why they have to be there?
Okay.
Not within these, like what you said earlier.
So basically, I said that for me to produce the voltage that links for the voltage that is produced, which is the voltage that is due to the flux linking both terms to be there, I have to have flux flowing in the core. For flux to flow in the core, I actually need magnetizing current to be present, right? N1 minus N1I1 minus N2I2 has to have a value. For it to have a value, I have to have some magnetizing current. I mean, the difference between these has to have a value. And we call this difference between them magnetizing current. Right? So it has to be there. It's something that will have to be there when the voltage is there.
So is this magnetizing current the same thing as the magnetomotive current that you were talking about last time?
The magnetomotive force. Magnetomotive force is like the voltage. It's both. It's N times I is the magnetomotive force on the primary side. N times I on the secondary side is the magnetomotive force on the secondary side. The difference between them is the magnetomotive force required to push current through. It's like superposition, right? I have voltage source on the primary side, voltage source on the secondary side. The difference between them is required to push current through the circuit, exactly like superposition in an electrical circuit. Yeah. Okay. No problem. Stop here.
7 weeks.